So as a reminder, I don't know how many of you are using this resource throughout the week, but I do actually put our lecture time, at least the audio of it, up onto YouTube, and it runs through my slides as well, up on YouTube each week. And so it is a good resource for you as you work through completing your homework assignments and the other elements of what's involved in this course. Now, I handed you all a notebook, and so what I would like for you to do in this notebook is to take everything that's due today, which are basically homeworks 1, 2, and 3, quiz 1, exam 1, lab 1, and tuck it all into one of the pockets of this notebook. And that way, as long as your name is on at least one of those papers, I know that all of those papers belong to you. It keeps it nice and organized. Ideally, I will have all of these materials graded and back to you when we meet next Wednesday. So if you can tuck your homeworks, your quiz, your exam, your lab into that notebook, that way just everything stays nice and organized. So ideally, I'll have these back to you next Wednesday, and next Wednesday I'll have a label on this notebook with your name on it. And from there, you'll be able to decide whether you want to hold on to the notebook each week or you want me to keep it each week, but you'll turn in your materials into it every week. So that way, as we exchange information, the likelihood of anything getting lost is diminished. Not completely eradicated, but diminished because of how we handle some of those. All right. I think schedule-wise, there isn't anything we need to talk about. Schedule-wise, I want to get a sense before you leave. I'll talk to each one of you. I want to get a sense of the amount of time it tends to take you as you work through the assignments for this course. On a typical week, how much time does it take you? And I want to get a sense from you, do you want more? Like, do you want additional practice questions? I'm not going to require anything more that you're required to do. So if I do give you anything more, it's not going to be required. It's just going to be like, do you want more practice? Because if you want more practice, I can write more questions, or I can point you in the direction of additional questions. Because I know what you're thinking. You're like, your questions don't make sense sometimes because you get answers that just are absurd, right? Like somebody's going to throw a basketball 250 feet as they're trying to make a shot. Like, where are they shooting from, right? But I can point you in the direction of some problems that always make sense. Anyway, so yeah, that's something I want to do. If I don't remember to ask you specifically before you leave, don't leave without having that conversation with me. So just note, even if you do want more, you want additional practice questions, I'm not going to require you to do additional homework problems. It would just be for you to have more practice during the week. In between our classes. Also, I don't think I told you all about this before, but if you want this to be more, like if you want some more college level physics, kind of you want to take the next step with this. I mean, physics is obviously already a college preparatory science class because physics is not required. You don't have to take physics in order to graduate. It's not even in the normal kind of sequence of science classes. It's one that you do when you're like, you know what, I want to go and I want to study something technical. But if you want it to be even more college preparatory, let me know. And I can begin to help you to kind of take that next step to where you're deriving some of the equations and it's not provided for you. You don't need to do that. For those of you that do. Last year, the dynamics were very different in this class. Are any of you seniors? Okay, so last year, the dynamic was completely different. There were 6 people in physics last year, and 5 of them were seniors. So it was like 4 of those 5 were going into engineering programs or into science programs at the college level. So like they wanted it to be a little bit more. If that's not something you want, it's fine. I'm not going to be sad. Okay, I don't expect it if that's what you're worried about. All right. Let me pray for us, and then we'll get started. Father, thank you so much for your incredible goodness to us. Thank you for the opportunity we have to pray and to know that you care about our prayers. I thank you for the reminder that even though you know everything about us, you know the desires of our hearts. And I know that the desires of our hearts are often wicked. And you know all of our imperfections and our feelings of loneliness and worthlessness and brokenness. Father, that you love us and that you're providing something that can fill us, can provide us worth and power and healing. And Father, I can't thank you enough for that. And I pray that as we're reminded of your love for us and what you provided in having a relationship with you, that it would draw us closer to you, that your Spirit would continually soften our hearts and make us more and more like Jesus, more and more like you. We ask this in the name of Jesus. Amen. All right, so this week and next, we're going to be talking about angular momentum. And so this week, we're going to focus on what is going on as something is moving in a circular way, and what does that actually mean in terms of force. Okay. Next week, we're going to talk about what does that actually mean in terms of what you can accomplish as that momentum then transfers. Okay, and we're going to begin to kind of build this idea that of what momentum is. So this week is called angular momentum, but we're actually going to spend very little time talking about momentum, and most of our time talking about angular motion, moving in a circular way. Next week, we're going to talk about momentum and transferring that momentum. All right, so our first question. How does circular motion compare to linear motion? And those are really your two types. Everything we've been talking about so far, it has been linear motion. So like projectile motion, that's linear, even though it doesn't move like a straight line, it still is linear motion. If it weren't for other forces like gravity pulling down, it would actually move in a straight line. Okay? With angular motion, we have things a little bit different. So yeah, we just know many objects do not move in a straight line. So many objects, cars, people, etc., CDs as they're spinning in a CD player. Do any of you even use CD players? Nice. Still got some use of CD players. Any of you use a record player? Yeah, record players are cool. But yeah, many things move in a circular way. And so these objects, even though they're moving in a circular way and are not moving linear, they still behave according to Newton's laws, especially Newton's second law. Well, all three of the laws. If it's spinning around a central point, it's going to remain in that motion unless there's another force. But Newton's second law is what we're going to emphasize. And Newton's second law can be summed up how? Do any of you remember how we sum up Newton's second law? Yeah. Yeah, F equals mass times acceleration. Force equals mass times acceleration. F equals ma. This is the summary of Newton's second law. Okay, and so even though it's moving in a circle rather than in a line, it still behaves according to that way, meaning that its force and its acceleration are in the same direction. Right? So, let's talk about this. Objects that move in circles accelerate away from the center of the circle. So if an object is moving in a circle, like a car turning around a curve, or a roller coaster going around a curve, or a person spinning, right? Like maybe, an ice skater, or a ballet dancer spinning, or a football player kind of looping around. Anything moving in a circle accelerates away from the center of the circle. And the acceleration is equal to this. The acceleration by which it accelerates away from the center of the circle is equal to v squared over r. And so what this shows, I'll tell you what these various things are representing in a minute. But basically what this means is that the object is accelerating. Oh, it says the object is acceleration. You'd have to go with either it has acceleration or it is accelerating, even with velocity remaining the same. And that's interesting, right? Usually we think of if something is accelerating, its velocity is changing, right? But things moving in a circle, they are accelerating away from the center of the circle, even when their velocity is remaining the same. It's just there's something overcoming that acceleration. And so v is the velocity, and it's measured in radians per second. Any of you know what a radian is? Do you remember it from, I don't know. I don't even know where you would encounter it. Probably not until Algebra 2, and I don't think any of you have done Algebra 2. That's fine. Have you done Algebra 2, Colby? Yeah. So velocity is measured in radians per second, and this is what a radian means. Basically, a radian is a portion of a circle. And each circle, a full rotation, an entire circle, is 2 pi radians. What's pi approximately equal to? 3.14159, and that's all I got. What do you have? You have some more, Stephen? 3 more? Yeah. That's all I ever cared to memorize. I know people have memorized pi to 100 decimal places. Why? I don't know. There are things that memorizing makes sense, right? Memorizing pi to 100 decimal places doesn't really make sense. Anyways, so each full rotation is 2 pi radians. And so what we're getting at here is radians is not a unit. Radians is actually a measurement. It's a number. It's a count. Okay? So radians per second can also be just written as rotations per second, or just nothing per second. So sometimes you'll see this unit, the velocity of circular motion, just written as inverse seconds. Seconds to the -1. I'm not going to write it like that because it gets a little bit confusing, but as you're kind of approaching other things moving in a circular motion, you may sometimes see that, just seconds to the negative power, -1. And what that means is radians per second. All right, and then R, I capitalized my R. R is the radius. Okay, so every object that's moving in a circle is accelerating away from the center of the circle with an acceleration equal to the velocity squared divided by the radius. And so let's work some problems. Okay, because you're just like, it sounds all fine and good, but it'd be nice to actually see it in action, right? Okay, so how is water in a bucket accelerating away from the center of a circle with circumference 53.6 centimeters if it takes 4.75 seconds to complete the circle? There's a lot here. And I told you this week it was going to be similar or simpler algebraically. That doesn't necessarily mean it's simpler to set up the problem. It just means the algebra is not as complex because you don't have as many parts that need to be added or subtracted away. So it tends to, once you have the problem set up, they tend to go a little bit more quickly because the algebra is not as involved. So what do we have? What are we given so far? We're given the circumference, right? The circumference is equal to 53.6 centimeters. And we're given the amount of time it takes to complete this, 4.75 seconds. And that's all we're actually given. Right? Okay. Now, what tools do we have? How do we typically measure the velocity of an object traveling in a circle? What are the units? Radians per second. And remember, radians is not a unit, it's actually a count of something. Yeah, but it's not, but overall radians per second is a unit. So that's one tool that we have. We have the ability to actually figure out the velocity. Okay? And that's, we also have a tool that says that the circumference is equal to 2 times pi times the radius. Right? That's not a tool that I taught you, but it is a tool that you would be provided. By the way, I don't expect you to have these kinds of things memorized. In the event that you have a homework assignment like this, you're able to go and to look things up. Okay? Even while you're taking an exam, you're able to go and to look things up. You have to complete them by yourself, and you have to make sure you present your answer in the proper number of significant figures. All right, and then what do we actually want? So these problems take a little bit of time to get set up, but once you set it up, the algebra is not as bad as some of the projectile motion problems. So what is the problem asking for? Yeah. So we have another tool that I didn't write down, and that's that the acceleration is equal to v squared divided by r. Right? We okay with that so far? Okay. All right. So we want acceleration, but in order to get acceleration, we're going to have to find velocity. We're going to have to find the radius, because we have neither. Do you agree? The problem gives us neither of those. And I gave us an example problem that's a little bit complex, and it requires us to do a couple of things for a good reason. And that's so that we can actually walk through all of these things together. So first, let's find the velocity. So the velocity is equal to radians per second. Well, how long does it take to complete an entire circle? 4.75 seconds, right? How many radians is a complete circle? Gave you this on the previous slide. 2 pi, which means our velocity is equal to 2 pi radians divided by 4.75 seconds. Do you agree with that? It takes 4.75 seconds to complete an entire circle, and an entire circle is 2 pi radians. So 2 times pi divided by 4.75 seconds, and we get that our velocity is equal to, by the way, this is exactly 2 pi, so you don't need to worry about limiting your significant figures based on this, okay, because it's exactly 2 pi radians. So we're going to limit our significant figures based on this. How many significant figures is here? 3. There are 3 significant figures here. 1, 2, 3. Okay, and so our velocity here, we'll give it in 3 significant figures, 1.32 radians per second. And again, radians, it's not really a unit, so you could just write 1.32 per second, but it's nice to keep the radians in there to just know what you're talking about. Radians, it's an actual count. It's not a unit. All right, so now we have our velocity, right? Are we ready to get our acceleration? Not quite yet, right? We need to find our radius. Okay, we have our tool that basically, if we're going to solve this for our radius, how would we do it? Right now, 2 pi is being multiplied by the radius. How do we eliminate it? If you multiply something, but then you also divide that something, you're essentially not doing anything, right? So we'll divide 2 pi away. If you divide 2 pi away from this side, you need to also divide 2 pi away from this side. And so we get our radius is equal to our circumference divided by 2 pi. Do you agree? Anybody not okay with this? Okay, we'll move forward then. So our radius is equal to our circumference, which is 53.6 centimeters divided by 2 pi. And we get that our radius is equal to 8.53 centimeters. You okay so far? Now are we ready to get our acceleration? We want our acceleration, but in order to get that, we need to define our velocity and our radius. Do we have our velocity and our radius? Yes, we do. We're ready to solve for our acceleration. So our acceleration is equal to our velocity squared, which is 1.32 radians per second squared, divided by our radius, which is 8.53 centimeters. And we get our acceleration is equal to 1.32 times 1.32 divided by 3. And we get that our acceleration is equal to, I just did this value here squared, okay, divided by this value here. And we get that our acceleration is equal to 0.204. And now we have to figure out what our units are going to be. Okay? And so here we have basically per second. Yeah, so our units are going to be a little bit strange in this one. So we've got basically this fraction of 1 over seconds. So this would give us 1 over seconds squared in this one. And so if we manipulate it algebraically, we'll get our units this way. Acceleration is equal to 0.204 centimeters per second squared. And so, which those units are nice, because acceleration should be something like that. Our acceleration due to gravity we did in meters per second squared. This is in centimeters per second squared, which is fine. It's just a little bit of a different way of dealing with this. And so another way that we could get around and make this a little bit simpler algebraically is if instead of radians here, we actually measured our velocity in centimeters per second instead of radians per second. It would have simplified this acceleration a little bit, because actually this isn't even true. It ends up being this 0.204 radians per centimeter second squared. Those are our actual units. Because centimeters on the bottom of the fraction when we divide this out, and seconds is also on the bottom of the fraction. It's on the top of our decimal, or not of our decimal, it's on the top of our fraction. However, it's on the bottom up here, right? It's radians per second, so seconds is actually on the bottom. So the units of this acceleration are a little bit weird, but that's okay. Next week we'll talk about how do you actually equate this into something that is more normal. And so instead of doing our velocity in radians per second, we'll actually convert that into meters per second or centimeters per second. These are for YouTube. Just before we leave, you can put everything that you're turning in today into that. So homeworks 1, 2, and 3, quiz 1, exam 1, lab 1 into there. And that way everything's contained. All right. All right. So in this next example, I'm going to show you the first parts of how we get away from actually providing an acceleration in units like this. Okay, so this next example, if a gear that has a radius of 0.156 meters and spins at 2,700 revolutions per minute, the gear has, and spins, what is the velocity of a point on the outside of the gear? Okay, so there are a couple of ways that we can solve this problem. First, let's just talk about what we have and what the problem gives us. So what are some of the things that the problem gives us? Gives us the radius, right? What is the radius? Yes? Radius is equal to 0.156 meters. Okay. It also gives us that there's 2,700 revolutions. So we could also talk about this as rotations per minute. 2,700 rotations per minute, meaning you're completing 2,700 complete circles every minute. Now tools. What are some of the tools that we have? We know that we tend to measure our velocity in what? What do we tend to measure our velocity of something moving in a circle by? Radians per second. Right? Maybe? So radians per second. And then what do we want? What is the question actually asking us for?
Velocity.
Yeah, it just wants the velocity. Okay, it wants our velocity. Okay, so now this is where we're going to set this up and we need to figure out how many radians are in 2,700 rotations. Each rotation is how many radians? 2 pi, right? So which means how many radians are there in 2,700 rotations? If each one is 2 pi, and we have 2,700 of them, we have 2,700 times 2 pi radians. Does anyone disagree? It's okay if you disagree. You just need to have a good reason why you disagree. Because you ought not to. Okay, so our velocity is 2,700 complete circles. Each circle is 2 pi radians. 2,700 times 2 pi radians divided by how many seconds? How many seconds are in a minute? 60. So every minute, which is 60 seconds, we accomplish 2,700 times 2 pi radians. Make sense? And again, I told you these problems are not simple to set up, but they're simpler algebraically, instead of having to do a lot of manipulation like you have to with the projectile motion. Did you have a question? It's on? Okay, so we'll do 2 times pi times 2,700 divided by 60, and we get that our velocity is equal to, now this is how many significant figures? It would be 4 if you put a decimal point there. Because if you put a decimal point there, you would know that basically only like 2,699.5 up to 2,700.5 would round to this value. Right? But if you don't have that decimal place there, can you know for certain that this wasn't actually 2,680 and got rounded to 2,700? Do you know that? Or do you know that it's not 2,740 that got rounded down to 2,700? right? You don't. So these zeros are not significant unless we put a decimal point, because now we're saying something very specific. So this has 2 significant figures, meaning that our answer should have how many significant figures? 2. Okay, 2. And so the velocity of any point on this here is 280 radians per second. Remembering that each time around the circle is 2 pi radians. And so if you're going to do that 2,700 times every minute, every 60 seconds you're doing 2,700 times 2 pi radians. Is that all right? That's a little bit different, because before the problems with projectile motion, we dealt with it long enough that it wasn't necessarily easy to set up the problem, but at least you knew what you were going to get. In this one, it's a little bit different, but then once you have it set up, algebraically, it's simple. So we're going to do a couple more problems after we talk about what does this mean in the way of force, and it will hopefully help you to kind of get used to setting these problems up. And then as we get into starting to work through the homework problems, again, feel free as you're working through these homework problems to ask any questions that you might have. All right, so our next question. What is centripetal force? What is centripetal force? So the thing you have to remember, if an object traveling in a circle is accelerating away from the center of the circle, there's some force associated with that, right? Audrey, you reminded us of the summary for Newton's second law. And what was that again? F equals ma. So which means that the force is in the same direction as the acceleration, right? So if an object traveling in a circle is accelerating away from the center of the circle, there's also a force pushing that object away from the center of the circle. How many of you have ever swung something over your head? Like a yo-yo or a ball on the end of the rope, and you can actually feel that there's a force pulling away from that, kind of wanting to tug that in a linear direction. And the way you can tell that there's a force wanting to do that, what happens when you let go? Does it keep spinning in a circle above your head? It does not, right? Once you relieve the force holding it in place, where does it go? It shoots off in whatever direction, depending on where you let go of it, right? And so if there's an acceleration pushing an object away from the center of the circle, there's also a force pushing an object away from the center of the circle. We call this force the centripetal force. The centripetal force. And because the acceleration here is equal to the velocity squared over the radius, right? We already talked about this. How much acceleration does that object have away from the center of the circle? Do you remember talking about this? Acceleration is equal to velocity squared divided by the radius. So the greater the velocity, the greater the force. Also, the smaller the radius, the greater the force. Which is the reason why have you ever been on a tire swing? If you're doing a big wide turn, it feels a little bit less intense than when you're doing small tight turns. So if the radius is smaller or the velocity is greater, the force is greater. If you're spinning in a circle, there's a force pushing you away from the center of the circle. And if you're staying put, your brain kind of moves around in your skull a little bit. And you feel that. And the fluid in your inner ear moves around inside your ear a little bit. You get dizzy. Right? And if you do small, tight circles, it's a little bit more dramatic than if you do big, wide circles. So once the object is allowed to leave that circular motion, it moves in a linear fashion with the same acceleration. So once the object is allowed to leave the circular motion, it moves in a linear fashion with the same acceleration. Now, our units for acceleration here are a little weird. We'll fix that next week. But it requires us to just have a better understanding of circular motion before we start talking about how do we reconcile this. Can I erase this one? Did you get a picture of it, Isaiah? Is that what you're doing? Okay. Okay. I'll put all this on the homework slides, or on the not the homework slides, but the lecture slides before I send them out. It is Isaiah, right? Yes. Because that'd be really bad if it weren't Isaiah. When I told you last week, I won't make that mistake again. Okay. So let's do another problem. So how much force does a car with mass 1,526 kilograms traveling at 45.6 meters per second experience as it enters a curve of radius 25.0 meters? Okay. And then we'll deal with the second question in a bit. So what does the first problem give us? What do we have? Or what are we given? Now you saw something right away, right? I mean, not right away, it's at the end of the first line. But what's our first number? Our first measurement? Mass is equal to 1,526 kilograms. Okay, what else do we have? This is a nice thing. It already gave us the velocity, right? What's the velocity of this car? 45.6 meters per second. Okay? So it already gave us the velocity. If it was traveling 45.6 meters per second, we don't have to go through figuring out the velocity of that car, right? It already gave it to us. Do you agree? What else does it give us? Radius. It gives us the radius. And this problem is just really nice. Okay, radius, what's the radius equal to? 25.0 meters. Not only is it nice giving us all of the values that we need to solve this problem, but it also gives it to us in all the normal units. Okay, what tools do we need? What tools do we have that connect mass with velocity and radius? What's the velocity for an object, or what's the acceleration of an object moving away from the center of the circle? Right? Acceleration is equal to v squared divided by r. Right? Force is equal to mass times acceleration. Right? We okay with those? So what does this problem actually want? By the way, it's okay to answer my questions. It's even okay to answer them incorrectly. It's fun. It's fun. It should be fun for you too, because it's a learning experience. Yeah, Josh? It wants force, right? Do we have everything we need to find force? Yes, but we need to solve for what first? We want force, but we need acceleration. So first let's solve for our acceleration. Our acceleration is equal to our velocity squared. Do we know the velocity? Yes, we do. 45.6 meters per second squared divided by, do we know the radius? Yes, we do. 25.0 meters. Okay, so we got 45.6 squared divided by 25.0 meters, and so our acceleration is equal to, and then so unit-wise, this squared is going to end up giving us meters squared, seconds squared, right? one of these meters is going to cancel out with this one, right? If you divide meter away, we can take one of those away. So what units would we be left with? Meters per second squared. Why is that convenient? What is the units of acceleration? When at least with acceleration due to gravity. Meters per second squared, right? We're left with those units. And so this one worked out nicely because it already gave you the velocity, and it gave you the velocity in meters per second instead of radians per second. So how many significant figures are here? 3. How many significant figures are here? Now this last zero is significant. Why? Because we've got a decimal point there. Okay? And so that tells us it tells us something about this zero. Okay? It's a little bit different than saying 25 meters. 25 meters means it could be anything from like 20 meters up to 30 meters rounded to 20. Actually, you probably couldn't, because if you're rounding to the nearest 5, it would be like anything from 22.5 meters all the way up to 27.5, right? If you're rounding to the nearest 5 meters. Whereas 25.0 tells you something specific. It tells you really this can only be 24.9 or 24.5 meters up to 25.4, right? So now this is significant. So this is 3 significant figures. This is 3 significant figures. How many significant figures should our answer have? 3. So our acceleration is 83.2 meters per second squared. Are we done? No, we're not. Why not? What did the problem want? It wants force. We had to find acceleration to get the force, but force is equal to mass times acceleration. What's the mass? (1,526 kilograms, right? Times our acceleration, which we have here. And we get that our force is equal to, oh my goodness. Okay, so this is 3 significant figures. This is 4 significant figures. 3 is less than 4, so our answer should have how many significant figures? 4. 3, I'm sorry, 3. Man, 127,000 kilograms meters per second squared. So that's our force, 127,000 kilograms meters per second squared. Did we talk 2 weeks ago about a unit that equals 1 kilogram meter per second squared? Our unit for force, named after the person who, named after Newton. So this would also be 127,000 newtons. That's a really, really strong force. It's a really strong force. Anyone know about how fast 45.6 meters per second is? It's a little bit over 90 miles an hour, which is why you don't typically go into a turn at 90 miles an hour. That's a really powerful force pushing against the car away from the center of the circle. So what's that force going to do? Make the car roll over. That's why you don't tend to take a turn at 90 plus miles per hour. Maybe you don't know that. Maybe you don't know that you're not supposed to take a turn at 90 plus miles per hour. But now you do. Although this is a pretty wide turn. 25 meters is almost 100 feet. So it's a fairly wide turn. And so that's a powerful force. All right. Is that okay? Let's do the second problem. The second problem in there is very similar to the first problem. It says, well, what about for a person that has a mass of 75 kilograms sitting inside the car? What force are they going to experience? Are they moving at the same velocity as the car? Yes, they are. You would hope so, right? Because if they're not moving at the same velocity of the car, they're no longer in the car, right? So they're moving at the same velocity of the car. Is the radius of the circle the same as the car's? You would hope so, if they're still inside the car, right? So the only thing that's different is what? Is the mass. And so now what do we have? What is the mass of this person? 75.5 kilograms. What is the velocity? The same as the car, right? Do you agree? Okay, velocity is the same as the car. And what is that? 45.6 meters per second. The radius is the same as the car. What is that? Are you imagining this image of somebody no longer moving at the same velocity of the car? Or are you laughing at something else? Okay. What's the radius? 25.0 meters. Okay? So what tools do we have? How do we calculate centripetal force? Force equals what? Mass times acceleration. What does acceleration equal? Velocity squared divided by the radius. What does the problem want? Same thing the other problem wanted, right? It said, well, what about a person with a mass of 75 kilograms, right? So the problem still wants mass, or sorry, still wants force. Should the acceleration be the same as it was for the car? Is the human and the car traveling at the same velocity? Yes, they are. Is the human and the car traveling in the same circle? Yes, they are. So should they have the same acceleration? Yes, they should. So we want force, but we don't have to go back and solve acceleration. We already did that, right? So our force is equal to our mass, which is 75.5 kilograms, multiplied by the acceleration, which was what? What was our acceleration away from the center of that circle? 83.2 meters per second squared. So 75.5 times 83.2. And we get that our force is equal to, how many significant figures should our answer have? 3. 6,280 kilograms meters per second squared. Or it's another way we can write that. What's another unit we can use for kilograms meters per second squared? Newtons. So 6,280 newtons. Why is the force less than the car was experiencing?
The mass is different?
Yeah, the mass is different. Okay? Force is a factor of both the mass and the acceleration. The acceleration is the same, but the mass is significantly less. So the person is experiencing less force than the car is, which is why cars are made of metal. People are not. Although if you tried to do this, you would that's a very significant force, way beyond the force of gravity. And so, let's see, what is the acceleration here is 83.2. What's the acceleration due to gravity? 9.80 meters per second squared. So this is like 8 times what the force of gravity is, which would mean the force that you would experience would be approximately 8G, which would be enough to probably make you pass out if you were that person in the car doing this, the force that you experienced. Which again, why you don't take a curve at 90 plus miles per hour, unless your body is equipped to handle that. New appreciation for stock car racers, right? Okay. Any questions on this one? This one is nice. It's a little bit straightforward. It gives us our numbers exactly the way we want them. This one doesn't. Okay? So if a person with mass 135.5 kilograms completes 1/4 of a circle with radius 13.5 meters and 4.5 seconds, what force do they experience away from the center of the circle? Well, it should say, does he or she? Do they? That's confusing. Now it's like that person's 2 people. Sorry about the grammar of this question. It's not technically correct, but we talk like that all the time. So, do we have? Then we have the mass. The mass is 135.5 kilograms. This is a big person. It's a big person. Okay, so the mass of a person, what else do we have? We have radians, right? It tells us that they complete 1/4 of a circle. How many radians is a circle? How many radians is a circle? 2 pi, right? So it tells us that we complete 1/4 times 2 pi radians in how many seconds? 4.5 seconds. And I know it's like, wow, that didn't seem so straightforward, right? Because it didn't just give me those numbers. And again, these problems are a little bit more difficult to set up, but algebraically they tend to be simpler. So it's like a trade-off, right? You can't have your cake and eat it too, as they say. Right? Either the algebra is complex or setting up the problem is complex. It tends to be one or the other. What else does it give us? Gives us the radius. And what is it? 13.5 meters. All right, tools. What's our tool, Audrey? Yeah, force equals mass times acceleration. What about for solving acceleration? What's our tool for that? V squared divided by r. And this actually, is our velocity, by the way. Velocity is equal to 1/4 2 pi radians divided by 4.5 seconds. We'll clean that up a little bit. We'll multiply the things out. Now, what do we want?
Force.
The force. But we've got to find acceleration first, right? So we're going to find our acceleration. Our velocity is equal to 1/4 times 2 pi radians per 4.5 seconds, quantity squared. Maybe we should clean that up first. Can we clean that up first? Because that's messy. Can we clean up our velocity first? I don't want to write all that in there. So let's do 1/4 times 2 pi divided by 4.5 seconds. And we get that our velocity is equal to 0. This is exactly 2 pi, by the way. This is exactly, we could assume it's exactly 1/4 of a circle. And so we'll limit it by this. How many significant figures are here? 2. So we'll present our answer in 2 significant figures. 0.35 radians per second squared. So that's our velocity when it's cleaned up. All I did was multiply 1/4 times 2 pi and then divided that by 4.5. Okay? Just cleaned it up. Is that all right? Okay. Divided by our radius. What's our radius? 13.5 meters. And again, our units are going to be a little weird. Next week we'll talk about how do you clean this up. But our units are going to be a little bit weird, but so our acceleration is equal to 0. We still need to limit it to 2 because this only has 2 significant figures. 0.12, and then our units are going to be radians per meters seconds squared. And I know the units are weird there. We'll clean that up next week. But is everything else besides the units okay? Meters is on the bottom of the fraction, so it needs to stay on the bottom of the fraction. Second squared is on the bottom of the fraction. Even though it's in the numerator, it's still on the bottom since it's radians per second, so it needs to stay on the bottom. Radians is on the top, radians will stay on the top. Okay? So I know our units are a little bit weird, but everything else okay? Now we have our acceleration, right? Can we solve for our force? Yes, we can. So force is equal to, what is the mass? 135.5 kilograms. And then times our acceleration, which is 0.12 radians per meter second squared. How many significant figures should our answer have? 2. So our force is equal to 17 kilograms radians divided by meters second squared. Those are some weird units for force, so we can't just simplify this and say newtons, because it's not a newton, right? It's a little bit weird unit-wise, but we have our force now. Next week we'll talk about how do you get from this to get it into newtons, our normal unit for force. But right now we can leave it like this. Is that okay? So now we've had 3 problems where we've gone and we've solved for our velocity given a portion of a circle. And sometimes that portion was a whole bunch of circles, right? We had a problem where we completed 2,700 circles every 60 seconds, right? In this one we did 1/4 of a circle in 4.5 seconds, okay? But either way, we've done that several times. So if, as you're working through your homework problems, you don't feel comfortable getting velocity in radians per second, let me know, and we can work through some more. I can solve you some more problems, record solving those problems and dump it onto YouTube, okay? Or work through something like that. If it's just a real quick problem, usually what I'll do is I'll write it out and take a picture and send it. Actually, if it's real simple, usually I just type out, think about this. But then if it's a little bit more complex, we can do it another way. If it's a little bit more complex, we can do a video and dump it on YouTube. All right? Please don't hesitate to ask questions if you have them. If you have not already done so,